everyone. Welcome back to the tutorial sections. So this is Zhihui from the Ohio State University. It's a pity that I can't join in person, but it's really my pleasure to give the lecture about learn the low-dimensional structures by deep networks. In the last lecture, Sam has talked about resources needed to ensure classify two manifolds. Now we will focus on the general classification of K-manifolds. And moreover, we will look inside the like deep networks. We will focus more on the learn the features and classifies. So let's first give the terminology we will use during the lecture. So we will use capital K to denote the number of classes. So capital K could equal to 10 for MNIST. Capital K could equal to 1,000 for ImageNet. For each class, we assume we have a bunch of training samples. So for example, we could have n different cat images. We could have n different dog images. So during the lecture, we will assume the dataset are balanced in the sense that each class has an equal number of training samples. They all have n training samples. Well, if not, we can easily use tools like data augmentation to make them balanced. Then for each training samples, we will label it. A common choice is so-called one hot labeling vector, which is a length K vector. It only has one non-zero element at the corresponding locations indicating its class membership, and the zeros at the side. We will have different deep neural network architectures, but most of them contains two parts. The first one is called feature mapping, that we map an input image X to, say, a wrong vector in a high-dimensional space. And then on top of the feature vector, we have a linear classifiers. There exist different architectures for these feature mappings. They share kind of like similar structures in the sense that they are layer-wise structures, and each layer contains an affine transformation, and then we have another layer on top of the previous layers. So each layer could be like fully connected layers, as in Sam talk, could be convolution layers, or could be like a transformer. So with this setup, the network output will simply be W multiplied by the features for each input X plus the bias vector. And then the training problem boils down to find the optimal parameters, which is the theta prime in the feature mapping, the linear classifiers W and B, by minimizing the difference between the network output and the one hot labeling vectors for all the training samples. And we usually a common choice is by the so-called cross-entropy loss, which we will talk in the next slides if you are not familiar with this one. And then we usually add a regularizer, for example, the weighted decay, which is a common choice, which is simply the L2 regularizers on the network parameters. If you are not familiar with cross-entropy loss, so here is a simple formulation of how we calculate the cross-entropy loss between the network output and the one hot labeling vectors. So for example, if the network output is so-called 1, 0, negative 1, we first apply the so-called softmax function to transfer this to a distribution, which basically that the first element will map to 60%, which says, well, this input has 60% being to cat, and 13% being to dog, and 10% being to panda. Now we can view the one hot labeling vector as also a distribution. Then we can say we just need to capture the difference between these two distribution probabilities. And this can be used, so this can be captured by the so-called cross-entropy loss, which in this case equals to a negative log the network output of the corresponding probability. So here, the network output of the probability cat class, which is 60%. So therefore, the cross-entropy loss for this case is negative log 60%. In this case, so from this, we can say that cross-entropy loss achieves its minimum when the network output probability is equal to the 1 hot label vectors, which means it will give us the correct prediction. With this setup now, our goal is to study the properties of the learned features and classifiers. We assume the network is well trained. Probably you would imagine there should be like different ways actually to characterize the properties. And in this lecture, we will take two perspectives. The first one is that we take one input and then we look at its features. We try to say what's the properties, the features we have. Okay, so we consider one as the individual property. The second one is that we put all the samples into the network and we take out all the features. And then we look together what's the features, what's the properties among all these features. We want to study these collective behaviors. It turns out that low-dimensional structures will emerge actually in both perspectives. Okay, so let me be clear what we mean by these individual perspectives. So here we use the AlexNet as an example, which is proposed 10 years ago and which is one of the pioneering architectures. So this AlexNet, it contains 5 convolutional layers, and on top of this one, we have 2 fully connected layers. So now that network is fully trained, and on the left, I plug into an image. So for example, here is a buoy image. And then we look at the features in each layer. Okay, due to the limited space, we plot the features only on the first convolutional layers, the third one, the fifth one, and the last layer. So we can say that the last layer feature, which is a length slightly more than 4,000. Well, so here each feature mapping, they have different shapes. What we do is we reshape it to a 2-dimensional space, to a 2-dimensional image, so that we can plot them. Even so, we can say so we can kind of like get much insight from these feature mappings, but there is a surprising phenomenon that in this feature plot, black means the pixel equal to, so black pixel means it has 0 value. So what we can observe is that if we look at the last 2, say, feature mappings, so I mean like in the bottom plot, what we can observe is that most of the pixels actually say are 0. Which means we have like sparse activations or we have sparse features. So okay, so this figure is actually obtained from the work by Mison and the collaborators. They actually they also plot the average activation densities of each layer over like training. So for each layer, you can say from left to right or from the dark to light blue. It means from the initialization to end of training. What we can observe is that after training, actually, the features tend to be sparse, in particular in the deep layers. So for example, if we look at the last layer, the last feature layer, actually, at the beginning, the features actually they tend to be very dense. They are not sparse. But after training, actually, they become sparse. Here we can say only maybe slightly more than 35% are non-zero elements. The rest of are non-zero elements, and the rest of them actually are 0. These sparse features also appear in other architectures like in VGG, Google Net, and SpaceNet, and many other architectures. These sparse activations also appear actually in like larger models, in the recent large models, and in particular, actually, the model become larger. That tends to be more sparser. That tends to be sparser. So let's look at a particular example, the transformers, which is one of the most widely large models. So a transformer, again, it contains a lot of layers, and each layer is corresponding to a transformer block. So within a transformer block, actually, it contains 2 components. The first component is called the self-attention layer, and on top of this one we have the MLP layer. So in this figure, we plot the features inside this MLP layer. Say right after so inside there's 2-layer MLP layers, and right after there's a relu unit. What we can observe is that, from the right figure is that most of them actually are sparse. So here, blue means non-zero elements and white means zero elements. So we can observe actually they tend to be quite sparse. Actually, only 1% non-zero elements in this feature mapping. This sparse active actions emerges in different transformers and data sets. So as shown in the left top figure, which appear in from sufficient transformers to T5 encoders and T5 decoders, and also for both natural language processing and vision tasks. Also, it also appears not only on the training data points, but also on the testing data points as shown in the top middle figures. It also, appears in different data sets as shown in the top right figures. Also, if we increase the network depth, say if we enlarge the networks, then it tends to be sparser as shown in the bottom left figures. And also, there's sparse features not only on the well-labeled data points, but also on mislabeled data points as in the top, so as in the bottom middle figures, and also on random images as shown on the bottom right figure. This sparsity can be exploited to improve, say, the training efficiency, to reduce the computation times, and also to improve the robustness and calibrations. So in particular, so for example, so in the work by Zhongli and Tong, which is the previous figures are from these figures. So previous figures are from these papers on these transformers. So what they did is that they simply, keep the top k largest values in each layer. For example, we just keep the top 128 largest values in each layer, which is quite sparse compared to the size of feature mapping. But if we look at the first column in the table, we can see actually there's no hurt to this natural accuracy. And by forcing the sparsities in each layer, exact sparsity in each layer, actually we could improve the training, the accuracy or the robustness to the label noise, and also to the input perturbations as shown in the tables and also shown on the right figure. Okay, so which also plots the different choices of k and the different different level of corruptions. What we can observe basically is that by enforcing exact sparsity, actually we could have better performance. While this phenomenon emerges, but there is a lack of mathematical justification for the emergence of why this happens or why the feature turns out to be sparse. Well, I think the Professor Thomas Project's talk on the compositional sparsity may provide answers to this question. Okay, so far we have talked about the sparse features in for each input. We look at the features, then we say, okay, they have nice actual properties, like the sparsity. Now we try to characterize the features, or in particular, we want to say how the features learned in each layer will facilitate actually our decision tasks. So for classification problems, we want to know how the features actually are separated or discriminative across different classes. So in that sense, we will study the collective behaviors of the last layer features of all the samples and classifiers. So we will first focus on the features just in the last layer in the last layer features, and then during the end of the talk, we will briefly talk about the features in the shallow layers. So just to be clear, what do we mean by collective behaviors? So say we just input n cat images and dog images and other images from other classes into that network, and we look we take out all the features. Okay, so we have a bunch of feature vectors. Then we try to look at their properties. Then we try to capture their statistical properties or their distribution of these features in this feature space. Okay, so for like this goal, the recent work by Papier, Han, and Dorner, they conduct a lot of like experiments, and they reveal common outcomes of the learned features and classifies across a variety of architecture and data set. And indeed, there is a precise mathematical structure within the learned feature and classifies. And we call this properties as the neural collapse property. So this neural collapse refers to the following three properties. First, it's called the within class variability collapse, which means the features of each class will collapse to class mean with zero variability. Or in other words, if we look at the features for each class, say all the features corresponding to cat, they actually tend to be very close to each other. They will converge actually to its class mean features. Likewise, if we look at all the features for the dogs, they also correspond to a single point. So now, if you think away, like all the features, actually, we turns out to have k different features. So therefore, all the features they live on a low dimensional space. They actually live on a k dimensional subspace. The second property concerns the distribution of these k class mean features. Actually, this says they will converge to the so-called simplex equal angular time frame, which means that the class mean features are linearly separable. They have the same length, and they have equal angle between each other, and the angle is achieved as the maximum possible in the sense that the cosine of the angle actually equal to -1 over k minus 1, which means the angle is slightly larger than 90 degrees. Well, why you may imagine why this cosine angle is the largest possible, why we can achieve each pair has larger angle, which is say 180 degrees. Well, it can't. So this is actually captured by this result, which says that if we have, imagine we have k unit length vectors u1 to uk in the dimension in a d-dimensional space, we assume the dimensionality d is relatively large, which means d is at least equal to k minus 1. Then, actually, if we look at the angles between each other, which is captured by the correlations between each pair of the vectors, then the largest these correlations will be at least larger than or equal to -1 over k minus 1, which means we can make them smaller than this value. This problem is also related to the or known as the optimal packings on spheres, or the or like the tennis problem, which basically you can think of like we want to uniformly put like a k points like on the sphere. And okay, and here, because the way assumes the dimensionality d is is large enough, then this corresponds to the simplest case of these problems, which we have closed form solutions. Well, so to show that result, we can simply use the following argument. We look at the sum of these k vectors, and we look at its energies. So like in terms of the square of the L2 norm, which we can expand it as k, as k squared in the product between each pairs. By like this simple argument, we can show that the maximum correlations between any pair will be at least larger than or equal to -1 over k minus 1. And we can show that this equality can achieved only when first say the mean of this k vectors equal to 0. Second one is that each pair has the same angle and the cosine angle equal to this value. The third neural class properties refers to the distribution of the class weight vectors. So the classifiers in particular, actually, there is a well alignment between the classifiers and the class mean, like feature vectors, in the sense that if we look at each row of the class, of the classifier with the metric W, then it points to the same direction as the corresponding class mean feature vectors. So this well alignment means that there is a self-dualities between this class means and this classifier with metric W. So this neural collapse property is preferred among every successful exercise in feature learning from the following two perspectives. From the information theory perspective, if we think of these features as the codings for the input, then this simplex ETF features actually is optimal Shannon code because they have the largest possible distance between each other. From the classification perspective, the simplex ETF features actually will lead to the simplex ETF maximum margin classifiers. Okay, so because each class has the largest margin to the decision boundary. Well, even so, this neural class property is preferred. A natural question is that we always train the network by iterative algorithm, like by gradient descent. Then why these iterative algorithms will learn these low-dimensional neural collapse features and classifiers? So to answer these questions, we will use tools developed in the non-convex analysis presented by Yuqian to understand these neural collapse properties. Now let's come back to our training problems, and we mentioned before that the network is contains two parts: a feature mapping and a linear classifiers, and we learn both feature mapping and the linear classifiers by minimizing cross entropy loss. However, this problem is usually highly non-convex, and it is hard to analyze and even to prove its convergence to global minimum. Well, the neural kernel analysis can guarantee that if we minimize the training error, if we minimize the training loss, the training error will converge to zero. However, we know that the neural kernel corresponding to the lazy training, which is different to what neural collapse will predict actually. So here we will exploit another perspective, and we will use another way to study these problems by studying a simplified problem. So motivation is that recall that this neural collapse is only about the learned classifiers W and the features. Therefore, let's feel these features as free optimization variables, which is so-called unconstrained feature model, which means that let's assume the features can move anywhere in the feature space. Then if we minimize this cross entropy loss, what are the features and classifiers we will get? Well, aside from simplifying the analysis, the rationality behind this unconstrained feature model is that modern networks are highly over-parameterized, that we can approximate actually any point in the feature space, which means that the features actually can move anywhere for any input. So this is also called the layer-peeled model. So we will use this simplified model, and we will show that this simplification actually will preserve the core properties of the last layer classifiers and features, which in particular, we will show that we observe this neural collapse phenomenon. So in the recent years, this neural so these unconstrained feature models have been used to understand that. To understand that neural collapse properties. Based on different setups. So for example, the work shows studies the one example per class, which means that we assume each class has a single training sample, and there is no weight effect, and we only assume the features live on the unit sphere, and then we look at what features we will learn by minimizing this cross entropy loss. Or other works will study this constraint formulations where we restrict the classifiers and the features within a certain region, say within a unit ball, something like this. Well, for all such works shows that any global solutions actually has null class properties. But what about the local minimum or saddle point in particular? This problem actually is a non-convex problem due to the bilinear structures within the weight. So within the weight metric W, and the classifier is H. And also the constraint formulations actually are not aligned with practice. To address this issue, so we will study this cross-entropy loss under this anchored feature models with this weight decay regularizers on both the features and the classifiers. This problem actually is closely related to the metric factorization problems presented in the previous lectures. So we will use the tools there and to study its global and local minimums and saddle points for our training problems. Let's first look at the global optimality solutions in particular. So our first result says that if the feature dimension is relatively large, and again, it is D is larger than or equal to now the number of classes K minus 1, then any global solutions to such training problems must identify null class properties. So in particular, the bias will equal to 0, and the features will collapse to a single point for each class. The features between the class mean features between each pair has largest possible angles, where the cosine angle equal to negative 1 over K minus 1. And the class and then the classifiers are well aligned with this class mean feature vectors. So again, here D equal to larger than or equal to K minus 1 is required to ensure the simplex ETF solutions, actually, as we mentioned before. So we know in the previous lecture said for a general non-convex problem, which is the case here, we not only have global solutions, we could also have local solutions. And we could also have a very flat saddle point, which means if we run gradient descent, we may easily get stuck at this point. Fortunately, for all our training problems, actually we can show that the problem has a very benign landscape. In particular, it has that any local solutions actually say are global solutions, they have these null collapse properties. And any critical point that is not a local minimum, indeed it is a straight saddle with negative curvature. Or if you remember, it means that if we look at the Hessians of this like functions at this point, it actually has negative eigenvalues. So that means that if we run gradient descent, you will easily avoid those points. All right, so now let's briefly talk about how we establish our global landscape analysis. So the proof idea is that, as we mentioned before, this non-convex problem actually is related to the metric factorization problems, and we can further relate that one to convex problems. In particular, if we let W multiplied by H as a new variable which is called Z, then we can show you that this non-convex problem actually will be related to the following convex problem in terms of Z and the bias vector V. And then the weight decay in terms of features and classifiers becomes the nuclear norm, or in terms of Z. So here the nuclear norm means the sum of singular values. So the first step we will show is that these two formulations, the original non-convex one and the convex ones, actually they have the same global solutions, in the sense that if say HWB is a global solution of the original problem, then W multiplied by H and B turns out to be a global solution of the convex problem, and vice versa. So the main idea is that if we look at the nuclear norm, which is the sum of the singular values of Z, actually this can be related to the weight decay of the factors W and H, Well, for any Z, we know we could have infinite many possible choices of W and H, such that CR multiplication equal to Z. But if we found the one which has the smallest energies for W and H, then its energy actually turns out to be the nuclear norms of Z, which is the variational form. So using this result, it's clear that if we minimize the non-convex problems, which kind of like minimize the weight decay in terms of W and H, it seems we are minimizing the nuclear norm for the convex problems in terms of Z. So second step is to prove the benign global landscape. So for this one, we will look at a critical point, which is not a global minimum of the original non-convex problems. Then, because it is not a global minimum, then Z, which equal to W and H, then ZB turns out to be not a critical point to the convex problem, because it is not a global solutions of the convex one and the convex one. If any point is not a global solution, it must not be a critical point, which means that this point actually does not satisfy the first order optimality conditions for the convex problems. Then by exploiting these properties, we can show that the hashing of the original non-convex problems at this point indeed has a negative eigenvalue. So therefore, this point is a strict saddle. Since the second step holds for any non-global critical points of the original non-convex problems, which basically says that the original problem has a benign global landscape, which means any critical point is a global solution or a suicidal with like a negative curvature direction. Therefore, if we combine these two results together, the global optimality and the global landscape, and then global landscape, then basically like following the like results we learned in the previous lectures, we know that because of this benign global landscape, if we run iterative algorithms like the gradient descent, you will almost surely actually you will converge into a local solutions, which turns out to be a global solution, and which turns out to have the neural collapse properties and classifies. Well, now we will conduct experiments with the practical networks, not on this uncontrolled feature models, to verify our findings on the later model. So we will use residual networks on CFR10 dataset, so which has 10 classes, and each class has 5,000 training images and have 1,000 testing images. Since we have shown benign landscapes on our simplified training problems, which means that if we run any local search algorithm, you will almost surely find neural collapse solutions. So now let's verify this one on predict networks. So in particular, we will train the ResNet 18 by different training algorithms, including the first order algorithms, SGD and Adam, and quasi-Newton algorithms, LBFGS. So here we plot the learning curves in terms of 3 neural collapse measures. The first, the left one, plots in terms of the within class variabilities. The second one plots in terms of the between class separations, or how they close to the simplex ETF. The third one captures how like alignment between the classifiers and the class mean features. The smaller of these quantities means the severe neural collapse. Since we will use the first measure very often in the rest of the talk, let's give the formal definitions of the first measure. So this first measure, it captures the trace of the covariance matrix, the within class covariance matrix, multiplied by the inverse of the between class covariance matrix. Well, so the within class covariance matrix, it basically captures the variance between each class features, actually how like each class are aware from the class mean features. So this you can think of as the noise term. So between class covariance matrix, it kind of like captures how separated the class mean features. If say are well separated, then this between class covariance tends to be large or somehow to be large, even though it is a metric. So therefore, this NC1, it captures actually how the features are collapsed and separated. If they are small, means the features are well collapsed and well separated. So with this, so here's the 3 learning curves which we showed before. Basically, I mean, like indicates that for all these 3 training algorithms, we always observe this neural collapse properties. So which means this neural collapse will across different training algorithms. Now let's see how this neural collapse depends on the training samples. So here we use the same CFR10, but we use a random labels, which means the labels are totally wrong or like not correct. Actually, we kind of like do a random shuffling for all the labels. And so here in the first in the left figure and in the middle figure, we plot the learning curves in terms of the within class variabilities and the self-duality collapse. So in each figure, we have different plots which correspond to different network widths. So from the top to the bottom, we increase the network widths actually from 8 to more than 2,000. So from these 2 figures, we can observe that as long as the network is wide enough, actually we will always observe neural collapse properties because they converge to 0. And so this is result on the random labelings. We also observe similar results actually on random inputs, which means each pixels are random. So on the right figures, we plot the learning curves in terms of training error. So we also say that we will achieve 0 training errors. So which, as we know, that the network will memorize training data, but it actually tells us it will memorize in a very special way, which means we have neural collapse properties. Well, so these neural collapse are so common, and the previous work by Papi and Donald actually shows that this property actually will lead to better generalization performance and robustness. We can also exploit this neural collapse actually for many other purposes. For example, to improve the training efficiency and memory cost, to understand the effect of loss functions, or to understand the transferabilities across different tasks. Okay, so we have seen that we always observe neural collapse across different training algorithms, different data sets. Then you may wonder why we need to learn like a linear classifier, because it will always convert to a simplex ETF. Well, actually, we don't need to learn the linear classifiers. We can just fix it as a simplex ETF. It could save us a lot of parameters, actually range from 8% to more than 15% for different architectures. The second one is that what about the feature dimensionalities? In practice, we usually use a very large dimensionalities, say feature D equal to more than 2,000. But here, our results actually shows that we can just use feature dimension D actually equal to the number of classes K, say K equal to 10 for CFR10. Actually, we will obtain the neural collapse properties. So this actually could first save a lot of parameters, because the last layer is, because the linear classifier is a fully connected layer. So here we conduct experiments on less than 15 on CFR10 with different setups. So in the plots, if we look at the left figures and from the top to bottom, the first case is corresponding to the standard one, or the default one, where we learn the classifiers together with, like the feature mappings, and we use the feature dimension D, which equal to more than 2,000. And then the blue curve where we fix the classifiers, and the green curve is that we reduce the dimensionality to 10, and the red one is that we both fix the classifiers as a simplex ETF, and we reduce its dimensionality to 10. And the left figure plots the learning curves in terms of the neural collapse. What we can observe is that So from the blue curves and the red curves, which corresponding to the fixed classifiers, actually we have, we have Sophia neural class, well, which is not surprising because we already fixed them as a simplex ETF. What's interesting is that if we look at the middle curves and the right plot, which is the learning curves in terms of the training accuracy and the testing accuracy. So if we look at them, we can observe actually at the beginning, the red curves actually were converging factor, which corresponded to fixed classifiers and a small dimensional features. And eventually we can say after training, actually they have identical performance. They have same training accuracy and same testing accuracy. So this actually tells us that the training with small dimensional features and fixed classifiers actually achieve on par performance with the large dimensional features and the learned classifiers. This is in contrast to the NTK theorem, which will require the feature dimensionality relatively large enough. So far, we have talked about the learned networks, based on the cross-entropy loss. So is this essential to the neural class? Or in other words, what about we use different loss functions to capture the network output and the one-hot labels? And indeed, there are various losses and tricks that have been proposed in the literature to improve network training and performance, and we will give several examples of them. So here is the so-called focal loss, which will put more focus on the hard examples by reweighting the cross-entropy loss. So here PT is network output probabilities for that class. So if PT is small, which means the sample is misclassified, then we add a relatively large weight. On the other hand, if PT is close to 1, which means the sample is well classified, then we add a small weight. So by doing this one, we will put more focus actually on the misclassified samples. So, or if we look at these figures, if we look at the left-hand side, that's 2 points. So there's the light one and there's blue one. So if the probability is small, which means it is misclassified, then there's a green point which has a much larger gradient than the blue curve, than the blue point. Okay, so another one is another common loss is so-called label smoothing. So the idea is that label smoothing, in label smoothing, we use a soft label, which probably we can say that, well, previous one we say we label the samples by 100, which means 100% is equal to a cat. Label smoothing says that, okay, let's not be so sure. Let's give some uncertainties for the label for the samples. So we will say, okay, now we will label these samples by 90% as cat, 5% by dog, and 5% by these pandas. Okay, so here says alpha, which captures the uncertainty you can think of. So this is called the soft label. Then the label smoothing, then we use the cross-entropy loss to capture the difference between the network output probabilities and this soft label. Another loss, perhaps the simplest loss you would imagine is the mean squared error loss, right? We don't involve any, say, soft max functions. The network output is 1, 0, -1. I just compare this to the one-hot label vectors, and then we look at the difference for each output, and then we sum them, and then we just use this as the loss functions. It's interesting that compared to cross-entropy loss, this mean squared error loss or its variant actually produce on-par performance on various computer vision tasks and the natural language processing tasks. So now a natural question is, which loss is better to use? If we look at the literature, we will find we may even get opposite conclusions in different papers. Some papers may claim that level smoothing is better. Some papers may claim that the cross entropy has better performance. So here in this table, we train the network with different training losses. So the 4 training losses we mentioned before, and the 2 different setups. So first, the law corresponds that we reduce the network width by 1/4, and we train the network by 200 epochs, which is a common choice. And in the second law, if we have enough resources, then we use a large network. We double the network width, and we train the network longer by using 800 epochs. So what we can observe is that if we look at the first law, we can say that, well, cross entropy loss is better, and it has better than MSE, and with 2 points better, actually, two points better. Well, if we look at the second law, by increasing the network width, actually they achieve all the performance increases, and they achieve similar performance. Actually, the gap become much smaller among different loss functions. So this actually implies somehow that all these losses will lead to largely identical performance when the network is larger and the chain longer enough. So to study this, so we will look at the uncontrolled feature models for different loss functions L. So we will study the loss functions under the so-called constructive properties. So it says that it basically refers to the following 2 properties. The first one is that if we look at the loss functions in terms of the case classes, it can be lower bounded by a new scalar function per psi in terms of the difference between the case output and all the rest of the, and all the rest of the output. And it achieves the equalities when the rest of the outputs they are equal. The second one is that if we try to minimize these scalar functions, then its minimizer is unique and its minimizer is like negative. So the intuition behind these 2 properties is that for the first one, we want to contrast, the case output simultaneous to all the other outputs. And the second one is that we want that the minimizer has the case output being its largest entry. So therefore, we have, a correct prediction. And and these properties, so for like these properties, we can show is that the loss function we mentioned before, cross entropy loss, focal loss, and the level smoothness all are satisfied. Then we can show that with the feature dimension D is larger than or equal to K minus 1, then all the losses with these constructive properties will lead to the same global solutions. In other sense, they have the new collapse features and classifies. So this, together with the previous result on the mean squared error loss, will tell us that all the one-hot labeling-based losses we mentioned before, indeed, they will lead to the same neural collapse features and classifies. Well, even though this result is established under the uncontrolled feature models, it somehow implies that if the network is larger enough and the chain longer enough, then we may get largely identical features on the training side, on the training data points, the neural collapse the neural collapse phenomenon. And moreover, we will use experiments to verify that actually all these losses will lead to largely identical performance on the testing samples. Now we conduct the experiments with less than 15 and using different training losses. So the most left figure plots the learning curves in terms of the within class variabilities for these 4 different training losses. And we can observe is that if we train longer enough, they all converge to the neural collapse features. The middle one and the right one plots the learning curves in terms of the training accuracy and the testing accuracy for these 4 losses. And we can also observe that actually they lead to largely identical performance. Now we now we study the performance and different setups with different network widers and training epochs to say the performance of different loss functions. In each table from the bottom to the top, we increase the training iterations from 100 iterations to 800 iterations. And from left to right, each time we double the network widers. Now, if we look at the left bottom like cells for each table, we can say that we do see some variabilities among each loss functions. However, if we train longer, then the performance will become better, and if we increase the network widers, all the performance will be increased. Moreover, if we just look at the right top corners in like say 4 tables, actually, first we can observe they are much better than the left bottom corner. Second, these 4 values actually they have very small variance, which means that by increasing the network widers and train longer enough, all these 4 loss functions actually they lead to largely identical performance on the test samples. Okay, so far we have talked about the learned features and classified. For the features we mean the last layer features. And we have shown that there is a neural class properties, which means that the features they are well separated and they are well concentrated. Now, a natural question is like that: if for the input they are not well separated, they are not concentrated, how does these features are like this separated or collapsed across each layers from the shallow layer to the deep layers? We can capture these progressive separations by the same neural collapse properties or by the neural collapse measures, which we mentioned before, which captures the ratio between this within class covariance and the between class covariance, and the smaller the more collapse. Here we plot a well-trained network and we plot its neural collapse across the layers. So from left to right, it means from shallow layer to the deep layer. Actually, it means each residual block. So what we can observe is that from left to right, actually the layer-wise training curve, it has a very surprising phenomenon. It kind of has a geometric decay, which means that there is a progressive separation and concentration among these features across the layers. So Professor Zhihui's talk I think will talk more on these aspects. Now a question is that how this well separated or how this progressive separation and collapsing will be transferred across different tasks or across different data domains. So here we try to numerically verify that this progressive separation is actually robust to the distribution shift. So here we pre-trained a ResNet on CEFA 10, and then we fix it, and then we evaluate this layer-wise neural collapse on the original CEFA 10 training samples, testing samples, and the CEFA 10.2 testing sample. So this CEFA 10.2, it has the same 10 classes as CEFA 10, but it has different actually training samples. So in the right figures, so here there's solid curves corresponding to the residual 18, and the dotted curves corresponding to the residual 34. And this, if we look at if we look at the solid curves from the bottom to top, it corresponds to the CEFA 10 training samples, the CEFA 10 testing ones, and the CEFA 10.1, CEFA 10.2 testings. So we can observe is that all these 3 curves, they have similar trend of progressive separation and collapse. Okay, and the second one is that the red curves actually say are slightly larger than the blue curve, and also the green curves, which means that distribution actually will that distribution shift actually will cause slightly less collapse, and which will turn out to give like slightly worse performance. Now, okay, so let's briefly talk about how this progress separation actually is transferred among different tasks. Again, we will use one example to illustrate this point. So we take a ResNet 13.4 pre-trained on ImageNet, which has 1,000 classes, and then we evaluate its its layer-wise neural collapse on CFR10, which is plotted by these blue curves. So remember that this model is fixed without fine-tuning. And then we will train a linear classifier on top of the features to look at its transfer accuracies, which is shown by these red curves. We can observe is that actually there are two phases in this layer-wise neural collapse on these downstream tasks. The first phase, which is from the first layers to the 11th block, actually we do observe this progressive decreasing actually on these neural collapse measures, which means that the first 11 blocks kind of like as a universal feature mapping, which can be used to progressive separation and collapsing. And then the second phase, after the 11th block, the neural collapse actually becomes increasing, which means that the pre-trained network actually, this part actually is specific to the particular data set, the ImageNet. So, okay, so this actually tells, implies, why projection height is widely used. It can help improve this transferabilities. And this result can also help us to develop efficient fine-tuning to improve transferabilities, and the team will talk more along these directions. So to summarize, so in these lectures, we have talked about two perspectives, that either from the individual perspectives or from the collective perspectives, where the low-dimensional structures will emerge in the learned features. So to summarize, in both, in the same lecture and in these lectures, we have talked about learning the common deep networks for the low-dimensional structures, either for low-dimensional data points or for low-dimensional features in several aspects. So in the next lecture, E will talk about a new approach actually for learning discriminative but diverse neural collapse features. And based on this, E will talk about designing deep networks architectures for low-dimensional structures. Okay, so thank you very much for your time, and I will be happy to take any questions you may have. Enjoy the workshop.